the process between 1 and 2, we have a process. The name of the process between 1 and 2 is a constant pressure process. You can see that is a horizontal line. The pressure does not change. What changes is the volume and the temperature. So between 1 and 2, we have a process called a constant pressure or an isobaric pressure. Constant pressure or isobaric, because the line is horizontal. Now the question is, at constant pressure, is the heat added to the system or is the heat rejected in the system? Now you look at the direction of this arrow here. When the direction is going to the left, it means that the heat is rejected at constant pressure. That is the importance of that arrow. So when you draw your sketches, your PV diagram, the arrow is very, very important to show the direction of flow. So in this case here, between 1 and 2, we say that heat is rejected at constant pressure. Now we move from 1 to 2 to 2 to 3. The second process of this cycle is a constant volume process. Constant volume because you can see the volume is the same at 2 and the volume at 2 and 3. But the pressure changes from 100 kPa to 400 kPa. So the second cycle, so the process is called a constant volume process or isochoric process. So you got the second process. Now you look at the direction of the arrow. It is going upwards. If it's facing upwards, we say that heat is added at constant volume, or heat is added isochorically. That is the name of the process between 2 and 3, the arrow. Now between 3 and 1, look at that arrow. The arrow is facing downwards, which means that the gas is expanding from 3 to 1. When the gas expands, the pressure drops, but the volume increases from 3 to 1. We will never have a situation where the pressure and volume increase or decrease at the same time. It's impossible. So if one increases, the other decreases. So between 3 and 1, the name of the process is called the adiabatic process. I'll talk about these processes after this slide. So what I wanted to emphasize is the direction of heat flow, as well as the state, the process, and the cycle. So this particular sketch, we have one cycle, we have 3 states, and then we have 3 processes. Now, let's have a look at this particular system. Now, if you look at this system here, it's actually an open system. Fluid enters at point 1 and fluid enters at point number 2. So what I wanted to indicate to you is, where is this formula coming from? Q is equal to delta U plus W for a process. I'm going to quickly derive it for you. Now for this particular system, is an open system. We say that energy into this system, or energy entering the system, is equal to energy leaving the system. Energy entering the system is equal to energy leaving the system. So what are those energies? It is the kinetic energy at 1 plus potential energy at 1 plus internal energy at 1 plus workflow energy at 1 and heat added at point 1, which is equal to energy leaving the system, kinetic energy at point 2, potential energy at point 2, internal energy at point 2, workflow, as well as the work input. So this is the general steady flow energy equation. So in this case here, for this particular system, we say this equation is called a steady flow energy equation, SFEE. But we are going to discuss SFEE when we deal with open systems. What I'm trying to show here is how did we come to a conclusion that Q is equal to delta U plus W. So because this is an open system, now we are dealing with closed system. Let's close this, close the system at point 1 and close it at point number 2 and see how this formula is going to change. Once you close at point 1, the kinetic energy is going to be 0 because there's no velocity. So KE1 is going to be 0. Similarly, at point number 2, KE2 is going to be 0. That is the kinetic energy equals the velocity. If there's no flow, the velocity is going to be 0. So kinetic energy is 0. Now the potential energy between 1 and 2, there is a potential energy, but the value of potential energy compared to other variables here is very, very small. So in most cases in thermodynamics, we ignore potential energy because the value of potential energy is extremely small, and therefore we ignore it. Therefore, PE1 and PE2 is going to be 0. Now, what is remaining here? U1, we still have U1. There is internal energy at point 1. There will also be internal energy at point 2. Now we move on to WF1, which is work flow energy. Generally, if there is no flow, now work flow energy is going to be 0 at 1, is going to be 0 at 2. So we are left with only 4 things. It is Q, it is U1, it is U2, and then it is work. So when you move U1 to the other side, we are going to say Q is equal to delta U plus work done, which defines the first law of thermodynamics for a process. Now the mass flow, only when it's open, is given by the mass flow at point number 1 is equal to the mass flow at number 2. But this is not for today, it's for next week when we do open system. But today, because there's no mass entering and mass leaving, we are going to ignore that. Now, for us to be able to answer the questions on the homework, I want us to have a look at this slide, which is sign convention. Now, when you are dealing with thermodynamics problems, you are going to have positive values and negative values. In practice, there's no such thing like negative work done or negative Q. The negative or the positive sign simply show us the direction of the flow. I'm saying that in thermodynamics, in real life, you can never have a negative work done or a negative internal energy. All that it shows is the direction of the direction of heat or the direction of energy. That's all it means. So we are going to start with the work done, which is most problematic to most students. Now, I want you to understand this so that you should be able to answer all the questions in tutorial 1. So, what does it mean when your work done is negative? In other words, you calculate, the question says calculate the work done on the system or by the system, and then your sign is negative. Now, when your work done is negative, that is the second one, you can see compression. It means that the gas is in compression, and we say that the work is done on the gas. Let's have a look at this sketch here, where you have a piston. Now, a piston here is, where is my pen? The pen. Here's a piston, and then you apply force on that gas through a piston. Now, this gas here is going to be compressed. It's going to be in compression. In other words, the pressure is going to increase, the volume is going to decrease. So what is happening here? It means that work is being done on the gas. In other words, the gas is being compressed. So the answer that you're going to get here is going to be negative. So when you do a calculation, you see a negative sign. You must know that the work is being done on the gas, and the gas is in compression. So you keep on compressing this gas up until the piston is at this point here. The piston will never go beyond that point. So you have a highly compressed gas in this area here. Now what happens? Because it's highly compressed, this compressed gas now is fighting back. It wants to go back to where it was. So when it fights back, it expands. It pushes the piston back to where it was coming from. When that happens, we say that work is done by the gas. In other words, now the gas is doing the work by pushing the piston backwards, and the gas is in expansion. Your answer is going to be positive. I repeat, I'm saying that after compression, the piston will move up to here. It can no longer compress this gas further. Now remember the gas here now is highly compressed. And when it's highly compressed, now it is fighting back now, it wants to expand. When it expands now, it expands and it pushes the piston back. Now, by doing that, it means that now the gas is expanding and the gas now is, the work is done by the gas on the piston. So in the expansion, when you look at the sketches, the PV diagrams, when the gas is expanding, you must know that your work done is going to be positive. And when it's compression, it means that your work done is going to be negative. That is the meaning of the positive and the negative sign for the work done. Now let's move on to internal energy. Internal energy, when internal energy is positive, it means that the energy is gained by the system. It means the energy is gained by the system. Now, when the internal energy is zero or less than zero or is negative, it means that the energy is lost by the system and we have a negative sign. And the last one is the heat. Now, when we have your sign is positive for your answer, it means that the heat is gained, is received or absorbed by the system. And in the last one, if your answer is negative, it means that the system has lost or has rejected the heat. Now, I want to go back to the first slide. If we have a look at the first slide here between 3 and 1, you can see that the gas is expanding. If the gas is expanding and I ask you, calculate the work done between 3 and 1, by the mere direction of this arrow, your answer is going to be positive. If it's negative, you must know that you made a mistake. You go back and check where you made a mistake. But if it's in compression, your answer must be negative. And if your answer is the other way around, it means that you made a mistake with your calculations. So let's discuss those 5 processes of gases. The first process is the one that we discussed in the first slide, which is a constant volume process. Constant volume process, we say volume is equal to constant because the volume doesn't change. It is called constant volume or it is called isochoric. The second one we also discussed in the first process, we say is a constant pressure process or isobaric process where P is equal to C. Pressure is constant. The third one is isothermal process. In other words, it's a constant temperature. I think I made a mistake here. It's a constant temperature process, not constant process. Constant temperature, where temperature is constant. The fourth one is a polytropic process. Nothing is constant for polytropic process. And then for polytropic, is indicated by what we call N. And N, this N here, by the letter N, small n, that N is called the index of expansion or compression. N is called the index of compression or expansion. And the last one is adiabatic or isentropic process. Now it is also denoted by what we call gamma. And for adiabatic process, no heat is allowed to enter the system and no heat is allowed to leave the system. In other words, Q is equal to 0 for adiabatic process. Now let's look at the PV diagram of the first process, which is constant volume process. Now, for all the processes except isothermal process, this value here, delta U, where is my pen? For delta U, this formula here, for all the processes is the same. The formula is the same except isothermal. So for all the 4 processes except isothermal, delta U is equal to mass by CV T2 by T1. But for isothermal process, delta U is equal to 0. I will explain to you why delta U is equal to 0 for isothermal when we do calculations. So delta U is equal to 0 for isothermal process. But for other processes, delta U is given by mass CV delta T. Now, for each process, we need to know how to calculate Q delta U, and work done for each process, for each of the 5 processes. Let's start with the first one. The first one is a PV diagram of a constant volume process. Now again, can you see that Q is capital Q, delta U is capital U, and capital W? So we are dealing with total work done, total internal energy, total heat. But if it's a small q, the small u, and the small w, we are dealing with specific heat, specific internal energy, and specific work. So the units for the capital letters is in kilojoules. If we are dealing with the small ones, it's going to be kilojoules per kilogram. So let's start. Q for isochoric process is delta U plus W. Now, W for this particular process here is equal to 0. So this W is 0. Why is it 0? Because for each process, work done is area under the curve. But because this is a straight line, there's no area under the curve, it means that W is equal to 0. Therefore, we can conclude and say that Q is equal to delta U for an isochoric process. That is all. So, but in the exam, I'm going to give you a formula sheet. The formula sheet, you can have a formula sheet, but if you don't understand what you are doing, you can still get wrong answers. But I'll give you a formula sheet. In the exam, you select the correct answers, so the correct formulas. So we are done with the first process, which is isochoric. Work done is 0. Delta U is equal to heat. The second one, it is the constant pressure process. And you can see from a PV diagram that the area under the work is going to be the pressure, can be P1 or P2, multiplied by change in volume. So this is a rectangle. A rectangle is going to be pressure multiplied by delta V. That is the work done for this particular process, which is P1 bracket V2 minus V1. If you don't have pressures, you can still use the following formula: mass multiplied by T2 minus T1. And ultimately, remember what I said? I said for all the processes except isothermal, delta U is equal to mCV T2 minus T1. Therefore, we can conclude and say Q is equal to mCP T2 minus T1. You don't worry about all of this. All I want to show you is where these formulas are coming from. I don't have to teach you or show you how to derive them, but just to show you, when we say that Q for an isobaric process is equal to mCP delta T, where is it actually coming from? This is where it's coming from. The third one is isothermal. Isothermal, remember, the temperature is the same. So the temperature at 1 and the temperature at 2 is the same. So from here, if the temperature is the same, this T2 is equal to T1, therefore delta U will be equal to 0. So the work done for isothermal process is the area under the curve. Area under the curve, because it's a curve, you integrate between the two limits, which is V2 and V1, which is C. What is C? Now, the important part of this whole process is that we are going to have 3 processes with the same curves. The curve for isothermal looks like this. A curve for polytropic also looks like this. A curve for adiabatic looks like this. All of them are the same. What is the difference here? The difference is that you must always write down the name of the curve. From 1 to 2, you can see that on the sketch, they didn't say anything about the name. So in the exam, if you did not put the name, you don't get a mark because I don't know which process it is. So what for isothermal, I want you to put the following, to say PV, sorry about my, PV is equal to C. So once we see PV is equal to C, we know that this is isothermal process. You don't have to write isothermal here, just write PV is equal to C. This is what we have to write for isothermal process. So we can see in this case here that this is an isothermal expansion. It's expanding from a high pressure to a low pressure while the volume is increasing from V1 to V2. So because delta U is equal to 0, for isothermal process, we will say that Q is equal to work done, which is PV ln of V2 over V1. The question is, which P is PV? Is it P1 V1 or P2 V2? It doesn't matter. You can either write P1 V1 or P2 V2. You are still going to get the same answer. You are still going to get the same answer. So whether you write P1 V1 or P2 V2, ln V2 over V1, you will still get the same answer. If you don't believe that, we will prove all these things when we do calculations. So this is the isothermal process. Q is equal to P1 V1 ln V2 over V1. Or you can say that work done is MRT ln of V2 over V1. Which T is that? You can say T1 or T2 because the temperature is the same for both states. And then we have the second last one. The second last one is an adiabatic process. How do you know if the process is adiabatic? The first thing is going to be the name of the curve. So the name of the curve here is PV gamma is equal to constant. So that is how you indicate an adiabatic expansion or compression. The mistake that they made here is that they did not put an arrow to show whether it's expansion or compression. So here is an arrow. It means that a gas is expanding adiabatically from point 1 to point 2, or is expanding isentropically from point 1 to point 2. So for adiabatic, remember what we said? We said Q is equal to 0. It means that for an adiabatic process, heat is not allowed to enter or to leave the system. So in this case, we say that delta U is equal to work done. Delta U is equal to work done. So for us now to get the work done for this process, we have to calculate the area under this curve. Here's the area under the curve. The area under the curve, you start from here to say that the area under the curve is going to be pressure change in volume, PdV. And then you continue. Ultimately, you get your work done for adiabatic process as P1 V1 minus P2 V2 over gamma minus 1. Or you can say MR T2 minus T1. The last one, I think I missed the polytropic. Yeah, there's no polytropic here. Okay, so because I missed the polytropic is similar to adiabatic. But the difference for polytropic, it is going to be PVN. PVN. Instead of gamma there, it is N is equal to C. Is equal to C. And also for polytropic, Q it is not equal to 0. So the difference between adiabatic expansion is gamma and N. So please, people, gamma is not equal to N. Gamma is not equal to N. These are two different things. Yes, so I think that should be all. The formulas for work done for polytropic is the same as adiabatic. The Q for polytropic is going to be work done is going to be this one, P1 V1 minus P2 V2 over gamma minus 1 plus MCV T2 plus T2 minus T1. That is the only difference. Whereas for adiabatic, Q is equal to 0.